Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question uncut. So we have an easy today. Yeah, also for yesterday, I forgot to press record, so that's why I didn't post yesterday. But like essentially, like you just do a try first, and you can kind of like get the answer. So let's look at today's question. It's called the sum of all subset XOR totals. Right, so we're going back to the bitwise stuff. So the XOR total of an array is defined as the bitwise XOR of all its elements, or 0 if the array is empty. So do we want like some subsets? What are our bounds? So we have very small bounds. It's only it's only 12. And also our numbers are quite small as well. So that means we can definitely brute force like if we have to. Hopefully we don't, but let's see. So for example, the XOR total is this. So given an array nums, right? So we want to return the sum of all XOR totals for every subset of nums, right? So well, the brute force way is definitely to generate every subset, but actually that way is even harder because you have to generate every subset. The easier way would be like, because I think like this is very important, right? But XOR XOR is commutative and associative, if I'm not wrong. So that means like A XOR B XOR C is equal to A XOR B XOR C. Commutative means that you can just change them around like this. So it's a bit mathy, but like with these properties, that means like if we have like some XOR like for some subsets, so we have like some XOR here, and then do we want XOR or do we want the sum actually? Oh, we actually want the sum. So maybe that would be a bit more trickier. But let's just have a think. Like it isn't easy, so it shouldn't be too bad. Right. So if we look at this, like surely we don't have to generate every subset, because like if we have to do that, it wouldn't be an easy, I think. Yeah, so let's see what tricks we can use actually. Right, so yeah, because we are adding them up. So we are doing like something XOR and then plus like something XOR. Yeah, we're doing the sum. I have to think a bit. Yeah, am I missing something very simple? Wait, so if there are like if some numbers are the same, we can definitely just cancel them out. Yeah, also another thing is like the numbers are quite small as well, so I'm not quite sure why that's the case. Well, I'm sure like there's an iter tool that generates all subsets, but surely we don't have to do that. Like surely there's a better way than like generating all subsets. Although it like I think it is easy because like there is probably just a function that just allows you to do that. Yeah, is there like what if so what if we sort this in like ascending order first? So like let's say for 156, like for example 2, like we can do something like if we sort it, it would be like 156, and then maybe we can look at like, yeah, maybe this is DP and like we are kind of just having like, because for subsets, when we, so like initially we only have one subset, right, which is like the empty subsets. Um, and then when we add an element for each of these subsets, we can either XOR like with the previous element, or like we can just keep it, right? So I guess like that's already a better start than generating all subsets, because n factorial is like the time complexity for n factorial is worse than 2 to the power of n. Um, yeah, but like in this case, like basically we're going to like double um like the number of subsets like every time. So like we will have one, and then like we'll look at five. Like we're gonna have like the original ones, and then like we'll add five to each of them. So like this will be the result. Yeah, but like in this process, do we have a way to store the like the result in some ways? So yeah, like because like we have to do it as a sum. I'm actually not quite sure if there is actually a way to do it. Yeah, maybe we do have to. Oops. Maybe we do have to like generate like all the XORs. Um, I'll think about it for like another minute, and if I can't think about it, I'll just do like this way, where you gradually add more elements in. Um, hmm. Yeah. So like the XOR sum here is just gonna be 0. Well, the XOR sum it's gonna be 1 here, and then so the sum for this is just gonna be 1. Uh, the sum here is going to be yeah, what is it going to be? Well, like we have 5, and then 1 XOR 5 is just 0, 0, 1, 1, 0, 1. So it will be 0, 0, 1. So it will actually be 4 here. So like we will have 5 plus 4 equals 9. Yeah, actually like because we are combining XOR with like sum, I don't actually think there is a wait. Yeah, I don't think there's a way like to actually convert, like if we can somehow convert like addition into like sum or and XOR kind of like operation, then uh then we can kind of like work around like with the XOR, and like we can use like these properties, like the commutative and the associative property, to kind of like work around. But like because we are using like addition, I think we will have to generate like all of these. And the time complexity, well, like we only have like 12 elements max, right? So that means like, and every time we are doubling, so that means like we'll have 2 to the power of 12 like elements at the end that we have to sum up. But yeah, let's just do that. It's not worth wasting a lot of time on this question, I think. So yeah, so we have so we need a current list first. So we'll put the empty subset in, and then now for x in nums. So we want to so for every yeah, we want new subsets. We'll just call it subsets maybe. So subsets. So for all the new subsets, like basically we just have to loop through like every number in subsets, and we just want to do so we want to append num XOR well, the current number we're looking at. So like in this case, like it will be like we get the old subsets that we have, like when we looked at 1, and then when we look at 5, we have to like do the subsets there as well, to like get the XOR of like those numbers. And like we can, like we don't have to actually store like all these subsets, because like XOR, like again, like we can, like it's associative, right? So that means we can just like keep XORing like the running XOR, and we will still get the correct answer. So after that, we just want to do extend with new subsets. And then at the end, I think we just want to return the sum of the sum of all these subsets XOR. I think that's how you do it. Okay, looks good. Right, yeah, as we can see, there are definitely like ways to do it in ON, so let's just have a look. Yeah, so of course you can use backtracking, but it's very slow. Yeah, what are the other ways they have? Yeah, so this way is very slow, obviously. Optimize backtracking. I think like this is kind of what we are doing. So yeah, this is what we are doing. Like we have a 2 to the power of n kind of algorithm here, because every time, like every element we see, we are doubling the amount of subsets here. Yeah, bit manipulation. Is this the quick way? Oh, it is the quick way. Let's have a look. So it wants to capture each bit that is set in any of the elements. Wait. So, and then multiply by the number. I will have to look at like the explanation here to understand that part, I think. So XOR, yeah, it's a bitwise operation. So we may be able to develop a more efficient approach. Yeah. So that's my suspicion at the beginning, but I couldn't find this. So working backward can help develop bit manipulation approaches. So we want to start by considering what bits are set. Right, so wait, why are we doing this though? Wait, this is like what bits are set. Huh. Right, so wait, but why is it like this though? Right, so if numbers are like 1 and 3, yeah, why is the output 6? Oh, in the result, so that's the actual answer, I think, right? Yes, that will be the actual answer. So they're kind of like working back, like looking at the solution and like trying to find some pattern. So what they see is we can observe a pattern that the least significant rightmost n-1 bits are 0. Right, that's very interesting. I have no idea why that's the case. So let's see if we can break the pattern by testing more inputs. So like n-1, right? So we can keep looking to see like why that's the case. So this means we can find the bits that need to be set, and then we'll have the result. Yeah, but why is that though? Are they going to explain? We can observe that most everything bits in the input, in the output are all 1. Oh, okay. So like it is saying that like all of these, like they have 1s on the left, and then they have like zeros. But like this shows that it's not the case. Like with this case here. Right, so we need to find ways to actually like do that. Yeah, so 1 1. Yeah, I think like they're looking at patterns now. Um so we have like yeah, it doesn't seem like there are like some like exact patterns that tells you whether like they are one or not. The most significant of the output minus all bits excluding the least significant. Okay, yeah, so that is just like showing the like the output against like the actual values. So every bit that is set in any of the elements is set in the output. Directly find the number of times each bit is set. Okay. I kind of see what they want. So like if you have a 1 and like you like basically you have to count how many times it is like it is in a subset, and like you kind of like use those to calculate like whether like how many subsets has like the first bit set. I think something like that. Um yeah. Yeah, I kind of get this, but like this is like very like unintuitive, and like honestly, like when I see the bounds being like so small, yeah, like when the bounds are so small, I don't think it's like worth thinking like so much, because like the answer will probably take a very long time to like actually find. Like especially you have to like believe in patterns and stuff. So yeah, thanks for watching, and I'll see you tomorrow. Bye.